manifold, the classical manifold, and today we'll apply the same method, the same algorithm for constructing maps for discrete systems. So when we talk about discrete systems, we usually think in systems where, let me put the we think about systems when we can where we can perform a certain type of operations. So we cannot apply any operation to a system. We think we cannot apply any operation to a system, but only so-called discrete operations. For instance, we will have a two-level system. So what we can do is switch up and down. For instance, this is a discrete operation. So we cannot apply an arbitrary SU2 rotation, but only a discrete set of operations. And this means a discrete system. In particular, we think that a physical analog of this is a system with finite number of levels, where we can apply only certain type of pulses, external pulses. So we transform states of the system one to another, not in a continuous, but only in a discrete way. So the content is very intense also. And by the way, here there's a very famous professor in discrete methods, Karel, so also you can direct to him. And I hope he will correct me if needed. And let's try to understand how we can work with discrete systems in general. What does it mean mathematically discrete system? So the general, tool we use to work with system with finite number of energy levels, where we can apply only certain type of transformation, are the so-called Z and X operator. These operators are very simple, really. Maybe they look complicated, but it is Z operator is a diagonal operator. We'll consider this operator as a diagonal in some basis, in the basis of eigenstates. So you just multiply each state by a phase, and the shift operator, which move one state into another. So actually kind of a starway operator, so we can jump from one state to another. And we consider system with d energy levels, so this phase omega is fixed to d squared from identity. These operators form the so-called discrete Pauli or generalized Pauli group, and they satisfy the commutation relation. So if we exchange z and x, we have this defect, which is the phase. And all these operators are cyclic in the sense that this power is just identity operator. Example, in case of three-level system, Z operator is just like this, and X operator is a cyclic operator moving from 0 to 1 to 2, and from 2 to 0. So in this sense, it is a cyclic operator. And there is another tool which is usually called finite Fourier transform, which allows you to go from Z to X operator, like in the usual continuous case, we switch from X to P. So in this case, we switch to Z to X by transforming one of those by the Fourier operator. This Fourier operator possesses several interesting properties. So in case, by the way, all this stuff we'll consider is applied well only to the very specific case when this dimension of the system is odd prime number. So it will not consider, for instance, d equal to 6. It is good. It is not good number. Only prime number. Later on, we go to the power of prime dimensions which corresponds to the collection of D-level systems. But here we'll consider only specific case of prime dimensions. And in case when these prime dimensions also it is 3, 5, 7, and so on, then this Fourier operator also possesses very important properties. So it is cyclic, and square of this operator is the parity operator. Actually, the existence of parity operator plays extremely important role in all this discussion. For instance, for two-level system, there is no such guy as parity operator, which leads to severe consequences, and all stuff which is related to entanglement, for instance, is somehow related to non-existence of power, power operator. All complications we have with classifying entanglement for qubit systems and qubit systems. Okay. Next, from next tool, from this Z and X operator, what we can design is are so-called displacement operators. These displacement operators play more or less the same role as tensor operators we considered in the continuous case. So what is this? It is a product of powers X and Z operator multiplied by some phase. This phase is still square root of that omega. So very strange construction, but this operator is constructed in such a strange way, so it is unitary operator. And in addition, they satisfy certain interesting properties we'll discuss a bit later. Well, these operators form, how many operators we have? Here we have d powers, so we have d squared operator, counting identity operator, and all these operators form a complete set of operators in the sense if we have any operator acting in the finite dimensional space, any operator we can expand in series of such displacement operators. So this is a very important property. So any operator. So this is a kind of tensor operator in the discrete case, and they satisfy these orthogonality relations. These are only tools we'll need in some sense. Now, okay, something two words about displacement operators. Yesterday, Frederick told us about commuting set of operators. So this is very close. So two operators, two discrete displacement operators commute. So each operator has two indices. One index corresponds to Z, another index corresponds to X. Shift and clock operators. So two operators commute when this symplectic product, in this case very simple, is 0. So, and in this case, when this symplectic product, yes, I will not stop here very much, since yesterday Frederick told us a bit about this. So these displacement operators, in addition, when this symplectic product is 0, they form a simple additive group. So if this 0, we have no phase, so the product is just the same displacement operators where we add the indices. What else? In addition, these displacement operators, they are similar to the group representation operator which, for instance, rotate our state on the sphere or displace in the plane. But in addition to those displacement operators, we have something else. We have similar to symplectic operators. What are such operators? These operators, they are called symplectic Clifford operators, that can change indices of our displacement operator in a designed way. So we can find an operator which change mn to m prime n prime. What are typical operators we have? We have so-called rotation operator. Now it looks quite abstract. So what does this mean? So we rotate Z operator, and as a result, we have Z operator multiplied by X operator. So we change from Z to product Z and X. And we have scaling operator, which also sometimes is called squeezing operator, squeezing discrete operator. So we transform that operator and we change it powers. Again, looks abstract, but when it's good to understand these things. So what is the interesting point? So we have two indices. Recall that any operator can be expanded on the series of such discrete displacements. Then these two indices, they play a certain very specific role. They identify our, say, position in the operator space. And on the level of this position in the operator space, the Fourier operator and the rotation operator and scaling operator, they act as a changing of indices. So we kind of move in the space of, in the operator space. Well, so what we did in case of in the continuous case. First, we introduce kind of group operator. So we can move somehow in our space, and then we introduced a concept of coherent state. There is also a concept of coherent states in the discrete case. So what is the idea? The idea is pretty much the same. So we choose some fiducial state, and we apply all displacement operators to this fiducial state, what we have in orbit. And this orbit we'll call coherent state. However, in this case, in the discrete case, there's a very important restriction. So we cannot choose any fiducial state, but fiducial state which possess this property. So we should never get average value of displacement operators equal to 0. If it's equal to 0, it is bad. So in continuous case, coherent states, what properties has a system coherent state? For instance, they resolved their identity, and in addition, we can use, in case of a continuous case, we can use coherent state as an operator basis. So we can expand any operator in over projectors on the coherent states, if you remember a bit, or maybe you learn it somehow. This means that there is a one-to-one relation between, remember, Q function, average of the density matrix over coherent state. Q functions, it is a function which carries the whole information about the density matrix. In what sense? In the sense that average value of an operator over coherent states has such a property that it can be, we can recover the density matrix from the Q function. So the same is here. So if we construct average of value of the density matrix over coherent states, then there is a possibility to recover the density matrix. So this is called informational completeness. Not only completeness, so any state can be expanded on the basis of coherent state, but it is informational completeness precisely in this sense. It is possible to recover it. There is a special type of coherent states which called symmetric informationally complete states, 6 states, which possess certain property. Maybe somebody saw it at some moment of your study. And here, for such a 6 state which satisfy this particular property, here is the explicit reconstruction form. Such a 6 state. There are several other possible fiducial states. For instance, eigenstates of Fourier operator is also kind of good coherent state. And there is a difference, however, between continuous and discrete systems. The difference is basically here. What we can do, recall that all the set of displacement operators, which is dmn, this n square operators can be split in set of commuting operators. These are set of commuting, so these D, which are labeled by M, M, L, M, where L is a number from 0 to D, all these operators, they commute to each other. This means that this set of operators with every L fixed generate a set of commuting operators. Such a set of commuting operators sometimes is called stabilizers in this discrete science. So the whole set of n square, d square operators can be split, and d plus 1 is disjoint, so there is no intersection of such sets. Important. So we have a finite number d square operators we can split in set of commuting operators, which these sets have no common operators, so they are disjoint. The eigenstates of each of such set is called, almost, they are bases, of course. The eigenstates form the so-called mutually unbiased bases. Somebody heard about mutually unbiased bases first time? So how would I say? The bases, the states corresponding to each commuting set, they possess very important property. In what sense? That if we take one element from one basis and multiply it by another element of the other basis, we have or 0 or 1 over dimension. This is probably I prepared something. I expected actually a bit different audience, more prepared. Okay, well, so this maybe it is not very well written here, and this would play important role in our discussion. So we have set of commuting operators. Set of commuting operators, set of commuting operators, set of commuting operators. So every set produces a basis. We call it psi1k. K runs from 0 to psi2k, psi3k. So if we multiply any psi1k to psi2k prime and take square of this, we have independently of k and k prime 1 over d. It is called unbiased basis. Such unbiased bases play a special role in all this discrete science. Actually, if somebody in future would work with entanglement, you will, in qubits or qubits, you will immediately meet these states. These states, the whole set of such states form a complete set. A complete set in what sense? That we can expand any operator in diagonal form. So any operator, any operator we have, we can represent in the following form. Here is a projector on such basis, and the factor of this projector is the probability to detect the state in such a state. So this is a diagonal representation of the density matrix, which is very common in applications. Okay, then let's go back. So we have a set of different sets of commuting operators. Each set has a basis. To each set corresponds a basis, better saying. And all these bases we'll call stabilizer state. Maybe also you heard about this, stabilizer states? Somebody? No? Stabilizer state, actually these are kind of very special state in quantum information science. I just don't know how to proceed. Let's proceed and let's go on. Let's go to the geometry. Maybe it will be more interesting to you. Yesterday, Frederick shown us a kind of geometry, kind of discrete geometry. It wasn't real geometry. Geometry, what means geometry? We have lines. We have a concept of intersection of lines, right? We can transform one line into the other, and so on. So actually, in case of discrete science, there's a possibility to build a discrete phase space. What is discrete phase space? Now, let's here. We have three-level system. So to three-level system, we put in correspondence, this is square, 3 by 3 square. In this 3 by 3 square, we can define the concept of straight line. For instance, what is straight line? Straight line is M and N here are axes, and A, B, C are some numbers from 0 to D minus 1. So this is straight line. So in this case, for instance, in 3 by 3 case, we have many lines, and a particular case of line is a ray which satisfies this condition, n equal to Lm. So L is just slope of the ray. So how many slope we have here? We have 4 different rays: horizontal ray, this ray, vertical ray, and this is also a ray. So we have 4 rays in this case. For each ray, we can put in correspondence parallel lines. What is a parallel line? Line has no intersection with the ray. So to each of these 4 rays, we can put in correspondence parallel lines. So this is real geometry. So we have lines which either cross in a single point or they do not intersect. So parallel lines or crossing in a single point. This is real geometry. As we agreed, to each ray we can put in correspondence parallel lines. For instance, each set of parallel lines, it is usually called striation. For instance, it has here horizontal striation. So this is a horizontal ray and 2 parallel lines to this horizontal ray. Okay? This is geometry. But now we can go further. This is the advantage of discrete stuff in comparison with continuous stuff. So we have this square. Each axis is labeled by 0, 1, 2. And to point, for instance, 2, 1, we put in correspondence an operator. And this is really new step with respect to continuous case. So we can assign to each block of this square an operator. For instance, here, 2m. M indicates z direction, n indicates x direction. So here we have operator z square x. Okay? So if we go back just for a minute and recall this displacement operator, which commutes when we change m and fix value of L, what is this? This is just an equation of a ray. So for the ray, this means that if we put operators in different squares of different blocks of this square, the operators which are located in each ray will commute to each other. And this is a real geometry, and it actually is a symplectic geometry of discrete systems. For instance, here is the same square. So along, for instance, this ray, what operators we have? Z and Z square, 0, 1, 2. This x and x square, this operator, 45-degree operator, zx, zx square, and the fourth ray is this. So these operators, operators labeled by points of the same ray, they commute to each other. And they do not intersect. Okay?
So the same color means operators to commute.
Exactly.
All of them commute with white.
Yes, this is identity.
Sure. So
Yes.
yeah.
Yes, here is the identity pair because since both M and N here are 0, so here is there is I should put an identity operator.
And you have 4 colors here and 4 lines.
4 colors
Same
here.
structure, well, so any prime dimension.
Any prime dimension.
Only prime.
Only prime dimension. No. Power prime dimension the same. Power prime dimension the same. You just label with element of finite fields. But the same. The construction is the same.
Do all lines have the same number of points?
Yes. All the lines have the same. All the lines, all the rays have the same number of points.
And the number of lines is equal to how it changes with
D plus 1.
n plus 1.
See? Number of rays. Number of rays, D plus 1. Each ray has D minus 1 parallel lines.
Yes, okay.
So in total, as we have here, the total, so we have here, for instance, D plus 1 rays, and each ray has D, they are total D minus D minus one parallel line. So in total, so I have D parallel lines in each iteration. More or less complicated. What is interesting here? Where is the geometry? This is not a geometry. This is a kind of fake geometry. Real geometry comes from possibility to apply symplectic operations. So what we have, for instance, in real geometry, we can rotate. We can change the scale. So have these operators. Those are called Clifford operators, but it doesn't matter here. The interesting point that in this case, we can do the same. For instance, if we apply this rotation operator to Z, what we'll have? We'll have Zx. We apply to Z square, what have Z square X square. What this means geometrically? We have this line, and there is a rotation which is represented by symplectic operator, which transform this guy into that guy, and so on. The only different operator is Fourier operator. What Fourier operator does? It transforms horizontal line into a vertical line. All the other vertical ray, all the other rays are related among them other by a rotation operator. A rotation operator is a symplectic operator which has simple algebraic form and simple geometric interpretation. So this is real geometry. Actually, this is also not very, very important. The important point here, that the same construction can be immediately transmitted to the prime power case and the most important n-qubit case. So in n-qubit case, we'll have exactly the same structure. So we'll have exactly the same squares, exactly the same lines and rotations, but some other operations in addition. So since this is the kind of trivial situation when we have just prime dimensions. Okay, there's some geometry here, but actually we more or less trying to understand what is going on. Okay, now, next step. We know how to construct map from continuous phase space to Hilbert space, and vice versa. It is done by a map. What is a map? The map is an operator which depends on the point of the phase space, right? What we agreed yesterday. So this is precisely phase space. Sorry, I didn't say something else here. Because when we talk about phase space, there are two different kind of associations, which is interesting and unusual from the continuous point of view. So we agreed we can associate to each block here and operators, and commuting operators and so on. However, let us recall to each set of commuting operators can be put in correspondence with a basis, with states, which we call stabilizer state. So now, instead of putting correspondence lines in this space with the operator, we can put them in correspondence with the eigenstates of such operator, right? Because operators, they commute, they have common basis. The only problem here is that to what state? So this set of operator has 3 different states. To what state we put in correspondence, for instance, this line? This is up to us. And this is a very big freedom which actually allows us to work with contextuality, for instance. In the case of multi-particle system. We have an additional freedom. So this is a kind of phase space, and it is phase space from 2 different perspectives, from the operational perspective and also from the state perspective.
Is the number of operators the same as the number of states?
No, because each state has a basis. So basis of this state. Right? So the question is, so we have here line, so this line, this ray is a set of operators, commuting operators. So we can put to this line a state. What state? There are many states. Exactly, there are many states, so, which we can associate in a different manner. However, let's recall to this line, there are 2 parallel lines. So the total number of lines, parallel lines, they precisely correspond to the number of eigenstates. So we can associate in a different manner parallel lines with eigenstates of the corresponding ray. For instance, here in this situation, so we have here Z operator. So this is a standard basis. So the computational basis. We have 0, 1, and 2. So we can associate this line with 0, with line with state 2, with line with state 1 or state 2. But this is not necessarily. This is one of the possibility we can employ. Maybe somebody else have. I understand there are different degrees of understanding. First degree, as we understand everything, no questions then. Second degree, we understand nothing, no equations either. And then we start to get something, then. Okay, so, but importantly, this ray corresponds to commuting set, but this ray, so this parallel line does not correspond to commuting set. The operators along this line, they not commute. So the association between operators and lines is 1, and the association between the blocks and state is different. Okay, so then since we have these 2 kind of associations, lines are associated either with operators or with state. This is a whole picture for the discrete, the so-called discrete phase space. So actually we can do basically the same operations here as in the common plane. Rotate, change, scale, squeeze, whatever you want. And here, and this is a trivial case corresponding to the prime dimensional case. In the power prime dimensional case, the situation is even more richer. Okay, so now let's go to the map. What we can do? What we can do is construct a map from the operator space to the discrete phase space. In what sense? We can take operator and represent it as a picture in this discrete phase space. Why? Because we have all the components for this. And this is done through a mapping kernel in the same way as we did it in the continuous case. So the mapping kernel, what is the construction of the mapping kernel? We have a very tiny record from yesterday. What is the construction? what is the general construction should be? The construction is kernel at 0 transformed by group representation operators, right? Right? Somebody had this memory? No, not very much. Okay, so what is this kernel at 0? Kernel at 0 has two components. One is the tensor operator, and another one is, we called it spectral function. The spectral function to some power, right? What was spectral function? It was an average value of the tensor operator over the fiducial state, right? So exactly the same construction can be employed in the discrete case. So, and we can construct basically the same type of map, in particular Q, P, and Wigner maps. The difference that here, this parameter S can take only 0 and plus minus values. It cannot not take values 1/2, for instance. It is forbidden in some sense. So we have, in particular, Q map. What is a Q map? When we map an operator to the average value of a coherent state. This is precisely Q map we have here. We had a P map. What is the P map? We can represent the operator in terms of projections on the coherent state, and the coefficient are the P functions. Same here, no difference. And in addition, we have a Wigner map. Wigner map is a self-dual map. Self-dual map means that we can compute the average value of any operator by summing the product of the same symbols. In contrast to the Q and P map, which are so-called dual to each other. Más o menos. Okay, the point is, such map exists. The construction is pretty much the same, with some specific differences, but we can do basically the same. Okay, now this is the how we can represent the kernels in terms of mutually unbiased basis, but probably this is not important here. Let's skip it. But here I have to talk a bit about something. Do you remember somebody learn about Hudson theorem? We briefly saw it yesterday. What Hudson theorem says? Not pure and pure. No. No, if the function is positive, this means the state is Gaussian state. Yes? If and only if, yes. It's if and only if, exactly. If and only, this is very important. If and only if, it's Gaussian state. There is an analog of Gaussian states in this discrete science. These Gaussian states precisely are eigenstates of these commuting sets, are the stabilizer states. The stabilizer states possess precisely the same property. The Wigner function of a stabilizer state is not only positive, it is a delta function in the phase space. So if I would like to plot the Wigner function, I did it for power prime dimensions. If I would like to plot a Wigner function of a stabilizer state, it would have the form of a ray. And this is it. There is nothing else in prime case. So stabilizer states, the states which are stabilized, which are eigenstates of sets of these commuting displacement operators. And if you want to represent such states in this discrete phase space, we'll have delta functions. Delta function, what means delta function? Ray. It is a ray. So here for instance, is the form of a stabilizer state in the phase space and in the phase space, so it is delta function. Even more, there is a theorem, the same. the Wigner function of a state is, of a pure state, is positive if and only if the state is a stabilized state. For pi-dimensional case, the only stabilized states correspond to rays. There is nothing else.
So is it fair to say that stabilizer states can be considered as analog of Gaussian states?
Absolutely, absolutely. Stabilized states are analogs of Gaussian states.
Yeah, those so-called magic states correspond to very non-Gaussian states.
Exactly, exactly. We'll talk about this in Oaxaca. In Oaxaca. Okay. So, and for instance, there's a notion of negativity. Actually, here's one of the fathers of this notion of negativity for continuous state. If the state is negative, means it is non-stabilized state. And stabilizerness actually means very important for the quantum information science, because stabilized state can be efficiently simulated on the classical device. So if we want to construct quantum computer, we have to go out of stabilized states. And this is a very big problem, because if you have 100 qubits, then to distinguish how far we are from stabilized state is a very complicated problem. It is a real problem, which is a cutting-edge problem in this sense. Well, do I have time?
Like 10 minutes.
Like 10 minutes. Oh, like 10 minutes. Very good. Maybe a bit more because of questions? 11, okay. So, what happens if we consider a composite case? What means composite case? Because this is, of course, all up to now, all those, it was just a game. And this is kind of more or less serious stuff. So what is the composite case? So we have identical D-level systems. What to do with identical D-level system? We saw yesterday that if you have already 4 qubits, then the number of possibility to classify anything becomes basically infinite and growing exponentially fast. So what to do in this case? In this case, it results that these diabolic mathematicians 300 years ago invented a certain language how to work with an n-partite system. Imagine this as a pure Galois guy invented, which started to use 20 years ago in quantum information. So the question is how we can label the state which is a state of n-particle system, and each particle still has d energy levels. How we label, just how we label it. We can label it with these strings, binary strings, for instance, or something a bit more complicated. But this is complication because we cannot, for instance, multiply strings. We can add them, but not multiply. So the language, the appropriate language, is to use language of finite fields. Finite fields that is actually can be studied, I think, in high school, because they require basically no preparation. So what is finite field? It is an additive group which is closed also by multiplication. This is it. It is linear space closed by multiplication. Of course, if it's a linear space, there is a basis. And there is a special operation there, which is called trace operation. So if it is a linear space, there is a basis, so we can expand any element of the field in the basis. Then what we do? We have a Hilbert space, we have state of n-particle physics, n-partite state. N-partite state, it is just a product, direct product of first particle, nth particle state. So instead of using L1, L2, and 3, where L is 0, 1, 2, 3, and so on, we'll use this lambda. And this lambda is just a composition of all these numbers in a single letter, which is element of the finite field, where we decompose. The decomposition of this element precisely gives you this standard basis in the standard computational basis. So, for instance, this is not quite true what I wrote here, of course, because too much to explain, but more or less, all these Z operators for n-partite system, which precisely Frederick showed us yesterday, here can be composed in a very simple form. similar to what we saw for prime case. So what we have here, diagonal elements of the basis, diagonal projectors. The only difference that these projectors are labeled by element of the field. And here, instead of omega, we have so-called additive character, does not matter. So this additive character basically is the power of the same omega, dth root of unity. The same for X-shift operators. We can do exactly the same. So we can add, but more or less, what we can do is multiply. We can multiply alpha by beta because the space is closed by multiplication. So we can construct real functions here. This allows us to work with our n-partite system as if it were a single system. This is the difference. So the same, what we can do, we can introduce the phase space. So I have no time, but if we beg Chrysomalis, so because this is just it again. So we can do the same. We can associate each point of the finite phase space, which x's are labeled by elements of the field, and put in corresponds to each n-partite operator a point in this finite field. And then what we have, let's just skip it here. Let's only see the picture. So what we have the same structure. We have lines, we have rays. This is a line, this is a ray, probably here. So the same geometry. So we can employ the same geometry. We can construct the squares inside big squares, small squares, and associate rays, for instance, rays in this big square with commuting operators, and parallel lines with eigenstates of such commuting operators. Where is the richness of this stuff? In the prime case, here's 8-qubit case, by the way. In the prime case, we had only lines. So we can put the operators only along the line. Line is very good. What would be ray, for instance? What would be ray in case of n-qubit case? Ray would be beta equal lambda alpha. Ray. Beta alpha indicate points in phase space. Ray. So operators along the ray commute to each other. We can multiply indices. So instead of doing something strange with binary strings, what we can just construct functions. However, the difference with the prime dimensional case, that a part of having rays. So what mean rays? Operators along rays commute. We may have curves in such a way that operators along curves commute, and stabilizers, the set of commuting operators. Now the classification of stabilizers is completely reduced to classification of geometric structures in this finite phase space. So for instance, here's a 3-qubit case. This is one arrangement of commuting operators, and this is completely different arrangements of commuting operators. So the same, this is for a yellow curve, this is a curve. This is a curve. So operators, if you take operators labeled by point, the phase space is the same. We just take different points and see what points commute to each other. These are so-called commuting curves in this case. The simplest case of commuting curves are rays. Okay, what else I can say to you? For instance, this is also a nice picture. So we have, remember that the whole phase space we can fill with rays, commuting operators. This is a whole phase space filled with rays. The 3 qubits, yes, this is 3 qubits, yes. Yes, because it results that qubit case is trivial. Qubit case is, you can, for qubit case, we can do the same, but qubit case is trivial. It is not interesting from the geometric point of view. And from algebraic also, it is, if somebody tells you about Q-treat, let's Q-treat and consider, he's doing something very simple. Let's of course, 2 qubits is very, very simple, very, very simple. Okay. 3 qubits, no, but 3 qubits is still simple because it's a special case. But starting with 4 qubits, then real problem arise. Okay, so and here is it is a curve. It is a curve. This is the equation for the curve. This is what, for instance, what is impossible to define in terms of strings. You just cannot define this kind of structures in different geometry. But in this geometry, you can define. Even more, there is an algebraic operation which allows you to construct, for instance, from this ray, that ray. There is a rotation, generalized rotation operator, which transforms not only rays to rays, but rays to curves. Let's go back. How different states, so we can, of course, we can do the map. We can map. We can see how different states are mapped in this finite phase space. And as I told you, for power prime dimensions which are not qubit, such a map is trivial in the sense that any map is factorized by particle, basically. Good here, good question. So in particular, the same Hudson theorem as we saw in prime case is applied to the prime odd power prime dimensional case. So stabilizer states, they have form of delta function, and these are the only state with positive delta function. In the qubit case, the situation is significantly more complicated, because in the qubit case, just a few words and I stop. In the qubit case, we may have stabilizer state, eigenstate of a commuting set, and plot it. And we plot it, and there are two difficulties. We can plot in different, for qubits there are different phase spaces. For instance, one of phase space is this, and this is another phase space. These are different phase spaces because they are based on different set of commuting operators. For Q-treats, although we do the same, but since the property of factorization, the plot looks just the same. Does not matter which arrangement we use. But for qubits, it is not the case. For qubits, we can take the same state and plot in different arrangements, and we have different pictures. This is the same state plotted in different arrangements. So this is that. By the way, what is plotted here is a stabilizer state. It does not have a form of a delta form. So probably, I don't know. 2 words. And I finish. In what is the difference between the kind of, to finish, difference between continuous and discrete case? In discrete case, there is a freedom. This freedom is related to two different points. One point is that we can arrange commuting operators in different sets and then produce different phase spaces, which leads to different representation of the same state. This is one freedom. And another freedom is precisely related to the association lines and states. So we can associate it in a different manner. And it results that in qubit case, there is always such an association that any stabilizer state can be represented delta function. And so it depends on the arrangement. So it is called in this language, this language, context-dependent picture. The picture depends on the context. What operators do you choose for representation? Okay, this is a kind of application of the Q function, interesting application of Q function. Q function can be used to distinguish. I don't think you have to take, I will upload later the presentation, so you don't have to take pictures. This is interesting thing, how we can use, because the question is, okay, I understand all this complicated stuff, finite fields and these manipulations, what for? What the hell I can do with it? So this is one of the applications, how we can use Q function to distinguish correlated and uncorrelated states. For instance, here the picture of completely uncorrelated states, and then insert a bit more correlation, so it becomes more and more correlated, so it becomes more and more dispersed in phase space. And we can use, for instance, sum of squares of the Q function to quantify such dispersion. This is just pictures how different states look like. And well, one minute. The last point, if we go to the experimental situation, I understand that's too much information. Go to experimental situation and say 100 qubits. What can I measure for 100 qubits? Frequently, you cannot measure qubit by qubit. So you can only measure something which is, you can only measure so-called collective operators. So collective operators means something which you can not distinguish. For instance, you have a Bose-Einstein condensate, and it irradiates. All these spins, they irradiate. So what you capture is a field. With this field, you can do many things, different kind of correlation functions. But the field emitted by the condensate do not distinguish. This field does not distinguish what atom emits what field, right? So you got information averaged over all possible permutations of atoms which participates in this radiation. So what we can do in the discrete K space, we can study not only discrete operations, but discrete collective operations, and map states to the collective space, collective phase space, and you can represent states in the collective phase space, which is very nice, but I think I don't have time. Okay, this is it.
Thank
Sorry
you.
for...
Let's thank our